just to remind you guys how to do this, like maybe number 28. That looks good. This is page 356. Because once you realize, can somebody tell me real quick why, and I basically just said it, but when do you use t-scores versus z-scores?
You don't know standard deviation.
Not that I have no standard deviation.
You know the sample, but not the
I only know the sample standard deviation, not the population standard deviation. What's got to be true, though, for step 1?
Normal distribution.
It's got to be normal. So if they tell me it's normal, how big of a sample could I have? If I know it's normal, I could have a sample of 2, 3, 4, right? So in section 7.4, this is the first time we're going to be able to get data lists. They've had to give me the sample mean and all that stuff before. Now they can say, here's a list of data. You calculate the standard deviation and the mean. You with me? Because before section 7.4, we couldn't use a sample standard deviation in our work. Now we can. So they can just give me a list of data. And thank God your teacher, even though he made you do this back in chapter 3, how do you get standard deviations now from a list of data? Calculator, right? It'll chew that stuff up and spit it out. Because we got more to do now. So I had to make you go through it first, just to get a feel for what goes into it. But now that we got all this other stuff to do with it, let's just get the calculator and give it to us. So that's what I'm going to review with you guys, is how to do that.
We've studied that, so it's like, I don't think we have another quiz, dude. Nothing no more test 3.
So the one I want to look at is number 28.
850.
So this is all about movie lengths and how long movies are. These are in minutes. Construct a 99% confidence interval estimate of the mean length of all movies given this sample. And I think further up, what do they have to tell me before I can do this problem? You just said it earlier.
It's normally distributed.
That is normally distributed. So it's somewhere up above this in the homework, they should say all of these are normally distributed. Okay. So I've got these formulas I can use when they ask me for a confidence interval. I obviously teach a lot of concept, and you can't get away from that with statistics. Statistics is concept heavy. But after I get through the concept, I always try to give you triggers as to when to do which thing. So when they ask you for a confidence interval, it's obviously got to be one of these formulas that has a plus minus in it. Right? That's a giveaway. And the other thing, who remembers what I told you about this? If I did tell you. The nice thing about these two formulas. The first two formulas. What's the really nice thing about those two, considering you can't have notes on your formula sheet? Yeah, this tells you when you know sigma, you use Z. When you know the population standard deviation, you use Z. When you know S, use T. So I don't allow you to have explicit notes, but the freaking formulas themselves are notes. That's nice, as long as you understand the formulas. How are we doing so far? So when would you use the last one? What would be the trigger to use the last one? When they ask you to make a confidence interval for the true percentage or true proportion. And one of the first two when they ask you to make a confidence interval for the true mean. And then you just figure out is this a Z or a T situation. Okay. How are we doing so far? Some of you guys look like, oh man, I can't believe I'm back here again. Come on. All right. So let's do this, and then I want to show you a couple examples from the real world, just to show you that this exact thing is used in the real world. That's one thing about taking an algebra class. You know, I always get that question, and I think I do a decent job, but it's really hard to tell somebody why they have to learn like terms when are they going to use that in the real world? This is easy as hell. When am I going to use it? When is that ever used? Well, I can show you any freaking journal in the world and show you where the hell it's used. I mean, that's pretty nice for me. But the first thing I want you to do is, what do I need for this then? What do I need to calculate to be able to create this confidence interval? All right, first thing I need is a z-score. And is it a z or a t? So which formula are we going to use? I know it's a confidence interval, so I know it's got to be one of these three. Which situation am I definitely not in? Let's start there.
The bar.
I'm not in this situation. Okay, not that one for this problem. Do they give you a standard deviation? So where will the standard deviation be coming from?
The sample.
The sample, therefore, I've got to use a t-score. Now you know on a test, I am not going to say, now use a t-score, blah, blah. So I'm trying to get you ready. This type of thing you've got to do to figure out, okay, he asked for a confidence interval. It's for a mean. It's not the last guy. My standard deviation comes from a sample. Okay, it's the middle dude. It's got to be a t-score. That focuses your attention on what you got to do, yeah.
Don't we also have to know?
Yeah, like I said, I think earlier in the section it should say it's normally distributed. Yeah.
I was gonna ask you, so what's that one that's above the division sign on the T one? What's that symbol?
Oh, that's trying to be an S.
Oh, okay.
Sorry. It was a very lazy S. And that is a slightly less lazy S. Okay. So how do I get this stuff from this data list? How do I get the mean and the standard deviation?
Calculate.
Calculator. What exactly do I do? Where do I put it?
The list.
In your list? Cool. Let's do that together. If you guys don't have the book,
I didn't know that.
write those numbers down real quick. I'm going to put those in the calculator. Okay. I'm going to take this away. I'll leave it. So those of you who can't remember, hit Stat, select Edit, the first option, and just start putting them in the list one. This is how we can get means and standard deviations from now on. Let me just switch over here real quick. All right, so I put all these in the list one. Then you hit Stat, Count. One verse stats only have one variable, the length of a movie. And it defaults to L1, so you just hit Enter. The default is L1. If you don't tell it a list, it'll just go and do L1. So hopefully, do you guys get that? Yes, good. That helps me out because I'm not sure if I put all the data in correctly. So the average length of a movie was just over 2 hours. Do you see that? 121, blah, blah, blah. Standard deviation was what? What's the standard deviation for this case? How many standard deviations does it tell me? 2. Why does it do that? One is a sample, one's a population, but you can't say, oh, I know the population, there it is. No, that's the calculator saying, I don't know if you just put a whole population in or if that's a sample. So we got to go as the human and say, oh shit, I need which one?
S.
S. It's a sample. We know it's a sample. Don't go, oh, the calculator did some magic and told me the population. No. Right? You can't all of a sudden, you always use z-scores because it always gives me a sigma, Jeff. I've had people tell me that, but that's not true. So what do we know so far? We know what do we got here? X bar is 121.75. S is 20.356. N is 12. Z-score for, not a Z-score, but a T-score, what do I need to get the T-score?
N minus 1.
Good. The degrees of freedom in this case will be
11.
11. 12 minus 1 is 11. And if I want a 99% confidence interval, can anybody tell me what alpha is?
99.
1%. Good. Alpha is the amount that's in the tails. Good. I like it. So alpha here would be 0.01 in 2 tails. Let me switch over to the T-chart. All this media is crazy. Come on. Unfreeze. Okay. All right, so which column am I going to use? First column. Degrees of freedom is 11. So it looks like my T-score is going to be 3.106. Cool.
Like you had.
So confused. Yeah, so I've got 0.01, degrees of freedom 11, so my T-score is 3.106. The Z-score would have been 2.575. You guys remember that? 99%. If you go all the way to the bottom, it actually says 2.576. It's a little bit better approximation, but it's still the same score. So what's true then? We said that the Z-score, if I can use it, it's one thing. If I can't use it, I have to be more conservative. I have to make my confidence interval a little bigger. So sure enough, all these T-scores are bigger. They're going to make my error a little bigger. Right? So that makes sense. And the smaller my sample gets, the bigger it's got to get to cover my answer being less and less and less certain about what I see. So 3.106. Okay, so these problems are obviously a little bit longer because they can finally just give us a list of data like the real world. Because we couldn't do this kind of problem before 7.4 because before 7.4 I had to assume I somehow magically knew the population standard deviation. That's crazy. I really shouldn't normally. So this is a little more true. And this is exactly what they do in the real world. So how do I put this together now?
Plug in check.
X bar, give or take, T times the standard deviation divided by square root of n. Square root of n was 12. So in 7.4, this is going to come from a different place, a different chart, but that chart is actually easier to read. These are going to possibly come from your calculator after you put the data in. So you're going to have a little bit more work in 7.4 to do. Not these, but this. So let's try to figure out the error. So I get this for the error here. I get 18, oops, sorry. I already did. I get 18.251.
Yeah.
18.252 for the error. Is that cool? Okay, so we know that with 99% confidence, we know that movies have an average of this, give or take, a little over 18 minutes. Cool? So it'll be 121.75, give or take, let's say 18.25. That'll make it nice with the 0.75. So it'll be, if you subtract this, it'll be 103.5. And if you add it, it'll be, what will it be, Jeff? 140.
140.
Thank you. So take just a second and try to write down what the conclusion should look like, and then I'll write it down on the board. Let's see if it matches up. Try to write what the conclusion to this would look like. So how does this conclusion start off? What do you say?
It can be 99% confident
We are 99% confident.
that the interval
I love it. That the interval
in those numbers
103.5 minutes to 140 minutes contains
the true mean
true mean. True mean what?
No, true mean.
True mean what? Bring back what it is. What was this problem talking about? Lengths of movies, right? True mean length of a movie.
For all movies or just samples?
Yeah, I can't remember if they were specific in the problem, but be as specific as the problem is. So this problem said, you can pretty much take exactly the wording from the problem itself. Where were you? There you go. Mean length of all movies, it says. Yeah, so obviously, mean length of all movies. I like it. Cool. So two things. You definitely have to have some units in your conclusion, and you definitely have to have reference to what the hell you're talking about. Is this the mean length of these mutant fish in this lake that some nuclear thing is doing waste for jumping? No, this is the mean length of all movies. You got to give me some physical, what the hell is it you just found? Something's that long. What is it? The movie length. Yeah.
It's a movie about nuclear fish.
Movie about nuclear fish, yes. Attacking some seaside town.
I have a question about the T-score, about the degrees of freedom. On the chart, it's like 2,000. So is that for a question that says 2001, where the sample size is 2001?
So the larger the sample gets,
Yeah.
the more space there is on the T-score chart between them. So and they are, on purpose, they're a little vague. When you get down to sample, if you had a sample of 112, what would you think your degrees of freedom would be to use this chart? 100. Technically, if you had a sample of 197, your degrees of freedom should be 100. But if you go to 200, I'll be okay with it. Because you always want to be as conservative as you have to be. And this table does not have enough resolution for in between 100 and 200. So how do you be the most conservative? You always round down if you have to. So if you had a sample of 2,587, you would use 2,000.
So if I have a sample of 2,000, I'd have to go down to 1,000?
Yeah, technically your degrees of freedom would be one less. But like I said, once you get really close, just go ahead and use that because there's so little change. When you get up to this length, I mean, look how little they change. They change by about 0.003 from 1,000 to 2,000. And right there, how far is it away from the actual z-score? 0.002. So that's pretty, there's some flexibility there. Okay, so I'll give you a little bit of a benefit of the doubt if you're not sure. If they give you some weird number that's between two, just try to remember you always got to round down to continue the process of being conservative. Yeah?
Is there a point in which we should just use the z-score instead of the t-score? Is there like a magic number that
Infinity.
Well, and again, I think I told you guys that some teachers and some books stop the t-score chart at 30. And I don't know if you agree with me, and it almost doesn't matter because I'm going to make you do this anyway. But if you look at 30, how far away are the t-scores away from what their z-scores would be?
0.27.
I mean, they're pretty far apart, aren't they? I mean, those z-scores aren't really that, those t-scores aren't really that close. So I completely disagree with that. But if you had a sample of 3,000, screw it, use a z-score. That's damn close to large. That's what I would consider large. How are we doing? I mean, this is not, and again, you should know this about statistics. It's not always an exact science. It has built into it leeway because it's trying to describe real life. Real life, you can't pin it down. I want to show you a couple things. Let me try to. Got some links in my email. Hold on a second. If anybody's interested, anybody majoring in psychology? I can't remember right now.
Oh, yeah.
Psychology. For example, because my first major was psychology, so I kind of have a leaning towards that because I love data. Psychology is all about data. And it doesn't have to be psychology, it could be music, it could be journalism, it could be whatever. If you go to a journal, and I'm sure you've had to do this for your English classes possibly or something, where you have to go to a journal to do some research. Type in Journal of Psychology. Psychology Today is a magazine, but that's the first thing that came to mind. But Journal of Psychology, Journal of Music, Journal of whatever. They'll have articles where they show you what I'm about to show you. So when I start, I've got two main things to show you. Don't worry, I'll switch it over here in a second. The first thing I want to show you is not as precise. It's not as interesting as earlier when we had country music versus depression, I think it was. But, I do what I can. This one is about red meat consumption and mortality. And just as a caveat, I eat red meat very much. Sorry, if you don't like that, it's good. But I don't eat as much as I used to. But I still eat red meat. But what I want you to really focus on, they tell you that they observed 37,698 men and 83,644 women. So that's damn good, right? I'm using freaking z-scores for this right here, right? That's large. Free of cardiovascular disease, blah, blah, blah. Updated every 4 years. So what they documented these deaths, and what looks familiar to us here, you can kind of follow what they're talking about. Cancer deaths, I'm not sure it's cardiovascular disease, blah, blah, blah. So you're not sure what multivariate might be, that's just a lot of variables. Lifestyle and dietary risk factors. The pooled hazard ratio, so you can imagine that that's probably bad if it's higher, I would think, the hazard ratio. So whatever that actually means, whatever goes into it, what looks familiar already? What's this referring to?
Confidence interval.
Confidence interval. So they have a 95% confidence interval. And they actually show us, this was their mean, this is their interval. Here's the mean, here's the interval for unprocessed red meat. 1 serving a day increase for processed red meat. And then, so you can kind of see the differences they're trying to show between eating unprocessed red meat, eating processed red meat, so forth. So even if you don't quite see what they're trying to say, what the point is, because it can get a little bit. Let me see. We estimated that substitution of 1 serving a day of other foods, fish, poultry, blah, 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 associated with a 7% to 19% lower mortality risk. That's crazy. But the thing I want you to really focus on is, like we just said, those are confidence intervals. If they gave us the data, we could actually calculate those confidence intervals ourselves. We know how to do it. That actually kind of kicks ass. Well, so here's one that's more related to what we're going to do today. That's related from chapter 7. Here's something that's related somehow to chapter 8. And I'm all about fitness because I just recently had a physical. So it's really in my head. My doctor's like, you guys don't. So this one's kind of interesting. Men, I think it was men. I can't remember here. Maybe it wasn't just men. All right. So they give us an idea of the ages. They even give us a bit of a confidence interval on that sort of, but it's sort of related to the standard deviation. BMI. I don't know if you guys know what BMI is.
Body mass index.
Good. So actually, that's getting up towards danger region, I think, if I remember correctly. And I'm not even sure what that was. Oxygen, I guess, oxygen in the blood, this might be what that is. Blood oxygen levels. So they did 60 minutes of exercise, or they did 60 minutes of rest. So this sounds like the setup for a drug study, right? You have a control group, and you have another group that has a treatment applied. In this case, the treatment was exercise. The thing I want you to realize, this is going back to chapter 1. They're trying to get us ready for this back in chapter 1. You can see some confidence intervals in here, right? This is like 7-2 confidence intervals on percentages. It's like decreasing in something, so that's why it's negative. Right here, no exercise alone significantly reduced the neuronal response to high versus control, blah, blah, blah. So they're getting all into it. But do you guys remember seeing this type of thing back in chapter 1?
Yeah.
This was when they were talking about what's statistically significant. So what that really means in this case is that's the probability that that would happen if it was just randomly happening. If it wasn't really an effect that the exercise or the rest had. What if it was just randomly happening, right? So it's sort of like if I did a study session with people, and those people got a higher score in that stats test. Does that really mean my study session affected them? Maybe not. But if there's a good enough p-value, if it was really unlikely that it just randomly happened, that they got a higher score, then that's evidence that it had an effect. It's not so likely that it was just random, so what's more likely? It actually had an effect on them. So we're going to get to the point where we can actually calculate this value ourselves. And if it's large, that's not evidence. If it's really small, that's evidence. So a really good question there is, well, what's small enough? Right? And that's where one thing we're going to talk about is how small does it have to be to show evidence for something? Okay. All right, so let's get into this. Let's see how this is going to work. And I don't know, sometimes people come into a stats class and they've already kind of discussed the class with people, the friends who have taken it before. And if that's true, has anybody heard of what we're about to get into is called hypothesis tests? Has anybody heard of that before? All right, good. Because normally it's something sort of akin to word problems for algebra students.
What do you got on?
Chapter 8. Chapter 8.
Chapter 8. So I'm going to be totally upfront here. I'm going to attack Chapter 8 in a very not well organized way, just so I can get through all the little bits and pieces. So I'm not going to be able to say at any point, okay, now I'm in A2, now I'm A3. So you guys just have to deal with that for a minute. Don't worry, I'm going to come back and really organize it once I get all the ideas kind of spewed out. Because I disagree with the way the book introduces things. I want to try to present it in my way, and then we'll come back and make sure that we get everything in each of the sections. Cool. So this is the idea I sort of got into the last time. I barely had enough time to really get something out. But if we felt gas prices were going back up. And we took a sample and found the average price of gas in our sample. To be honest, I haven't bought gas in a while. I live a lot closer to school, so I'm not buying gas as often as I used to. Right now it's what, like
4 some? 420, dude.
409 for the Costco.
Yeah.
oh, it's 4 what now?
I get it, sir.
415. So let's say we think it's 420, and it's the last claim we saw, the accepted to be right now 415, and we think it's gone up, and we find a sample, we see, sure enough in our sample, we see it's 420. Why can I not stop right there? You guys kind of get with me? So let's say that somebody said, gas is like 415. We heard that in the news this morning. We're like, they're wrong. I'm going to go take a sample, and I got 420 in my sample. Some of you guys are a little stuck on that number, but yeah. I noticed that. That's just totally twisted.
It's still fresh in our memory, but it's quickly
I understand that the day was recently celebrated, I'm sure, in several different ways. And why can I not stop right there and say, I found a sample's bigger than the 415, so screw you guys, you're wrong. Why can I not just say that here? I took a sample, I found an average gas price of 420. They said it was 415.
There's a chance that your sample isn't very good for the whole population.
More than that, actually. I mean, you're right, though. It's not that it's not very good. I could have picked it beautifully, but there is a chance that just by random picking, I happen to pick some that were higher. With me? It's just a sample. I really want to get this idea in your head right now. In order for a sample to prove something, in this case, what's my claim? Can any of you guys, what is my claim? Why did I go take a sample of stuff? What's my claim?
Gas price is going up.
Gas price is higher, right? Higher than what? Now be more specific. Higher than what?
415.
415. So I'm claiming that the average gas price of all gas in San Diego, let's say, that's why I'm using the mu symbol, right, is more than 415.
About regular or mid-range?
I think it's regular, right?
Yeah.
I'm really doubting a lot of us buying that high level stuff. Okay. There's always those gas stations out in Carmel Valley or something that's 460 or something. Who the hell's going there? People that don't care. Anyway, people live in Carmel Valley.
Exactly.
They're screwed. So the claim is that it's higher than 415. In order for a sample, in order for it to be enough evidence that that is wrong, it's got to be sufficiently higher than this. If I took a sample and found 416, you're going to say, oh, screw that. Too close, right? What about 417? Still a little. How do I tell how far enough is far enough away? What is it that I haven't told you? There's actually two things I haven't told you that would help figure out if those are far enough apart.
Standard deviation.
Standard deviation. And I love it. Beautiful. I didn't tell you how large my sample was. If my sample was 2, well, screw me. I mean, come on, Jeff. Haven't you learned a damn thing? If my sample is 200, hey, that's pretty damn good then, maybe, right? But it also depends on, I need to know the standard deviation. Let's start with sigma, and I need to know n. Does that make sense? I mean, when I first introduced standard deviation, I really tried to get it in your heads that it was a measure of distance. And z-scores use that. So standard deviation is like the tick marks on a ruler, and z-scores when I lay that ruler down. So z-scores tell me how far apart things are. So if to show evidence, I have to show that a sample is far enough away from some given number, that's z-scores. Z-scores tell me how far apart things are. So let's say that the standard deviation is Jeff, you could do it, 13 cents. And let's say my sample was 34. So first off, am I allowed to do anything with this?
No.
Why not?
We don't know if it's normally distributed.
Yes, we do.
We do?
Yes, we do. Because n is Central limit theorem says normal, enough. Cool? So I covered my S there.
You haven't specified the confidence interval.
We're not going to create a confidence interval. We're going to do something different. We're going to do this bad boy here. I'm going to what I'm doing right now, just to let you know, there are 5 steps to a hypothesis test. I'm focusing on 2 of them right now, because they're the ones we can do right now. You don't need any explanation. None of this is really new, except for the idea of how to show evidence for something. That's a little new. But what we're about to do is calculate a z-score. That's not new. How would I calculate the z-score for this situation? I know that x bar is 420. I know that the mean is accepted to be 415, so that's what I use. And let me try to speak to that for a second. If somebody says that the mean gas price is 415, and we think it's different, and I'm sure you've heard this before, you would say, okay, assuming you're right, let's assume that it is 415. And then you go take a sample and you say, well, look what I just found. You're silly. So haven't you heard this situation where, assuming you're right, how the hell did that happen? Oh, shit. So that's what we do here. People get a little hung up on, why do we say it's that when we're trying to prove it isn't? We say, assuming that it is this. Let's just assume it is. So the mean is 415. Population mean. I'm going to find a sample to show that that's wrong, or try to show that it's wrong. I have no idea how this is going to come out because I just made the numbers up on the way. Let's see what happens. What's the first thing I need before I calculate a z-score? What do I need to do to something because of something else I did in this problem? What needs to be adjusted still?
Standard deviation.
Standard deviation. The new standard deviation is the old one over the square root of the sample size. So it'll be the 0.13 divided by the square root of 34. Like 0.022 something.
1.0 and then 3 twos.
Oh, cool. Like, you guys get that? 0.0222? Oh, I guess we wrote it down, but anybody else do it? No. Okay. We'll go with that. So now the z-score will be my data point minus the mean, and see how that's capturing the idea of how far apart they are, of course. I want to see how far apart they are relatively, divided by the new standard deviation. Now in the book, real quick word on the book here. In the book you'll see this formula, which really exceptionally sucks, because a lot of people don't put that in the calculator correctly. But do you see how I do this on the side? So I don't have like fractions inside of fractions, right? If you want to do this formula, you have to do this. Not draw a circle and erase it, but you have to do this in your calculator. With me? Because you got to tell it what the top is, and you got to tell it what the bottom is.
And the bottom has the top and bottom.
That's fine. It's on the bottom. It's all that matters. So what do we get for a z-score? It'll be 420 minus 415 divided by 0.0222.
2.25.
Say again, sorry?
2.25.
2.25. That's kind of funny. I like, that's the way I would have designed this if I would have actually designed it. What's your gut reaction to that? Is that far enough away? Do you have enough information to figure it out? What's the only thing you really have right now that we've talked about that tells you if that shows you something is weird about that data point we got?
More than 2 standard.
It's more than 2 standard deviations, right? And that's directly related to like a 95% confidence interval, because that would have 5% on the outside, true? From empirical rule, 95% inside 2, 5% outside. Are you guys semi with me here? So on the surface of this, it seems that that is enough information. That is enough evidence that what is true.
It's unusual.
That is unusual, assuming that this is true. So let me say the whole thing we just found. We pretty much completed this. The core of hypothesis test is what we just did. Assuming that it is 415, how could I go get a sample randomly that is that far away from your 415? So screw you, you're wrong. With me? You don't say that in the paper when you write it, but you think it. You guys kind of with me here? So if they think it's 415, how can I get something so far away from it? If it is 415 and I take a random sample at 34, shouldn't the average be close to 415? Was it close? Not close enough, according to what we know. With me? A little bit. Okay. That's the idea of a hypothesis test. And within a hypothesis test, they actually tell me how far enough is far enough away. It isn't always 2. It's been 2 for us before now, but now it changes based on how bad it is if you make a mistake. You can actually change the level of what's called the level of significance. How far away do you have to get? Okay, so I'm going to try to do this. I'm going to try to do an entire problem with you guys. Then I've got a handout that actually explains each step that we've done. So you can kind of have it as you do your homework. Oh, shit. One last thing I forgot. What was that z-score we got on there?
2.25.
So, remember that P that they were talking about? Remember that from that paper I showed you guys? And from chapter 1? So that's for a different problem. Let's figure out our own p-value. The p-value would be the area in the tail that our z-score makes. It kind of is a measure of how likely this thing is to happen. The percentage in that tail kind of tells me how likely this thing is to happen. So can anybody tell me how much area is in that tail? Where would you look to find that?
We looked at the Z chart.
In the z-chart. So you look up 2.25.
And then 1 minus that.
Exactly. So if I look up 225, I get 9878. If I do 1 minus that, I get 0.0122. So there's about a 1.22% chance that I'm wrong of what I found. There's a 1.22% chance that that would happen on its own. That's what the p-value means. So in this case, we'd say p equals 0.0122. That's what we would put in a journal article when we're doing this, because then other people can make up their own mind. Is that big enough? Is that too small? What is that? They can make up their own mind. I just report what we found. Okay. So for some people, that's not good enough. Let me take one right out of the book here, section 8.4 actually. So for a minute, I'll be specific on my sections. Just to try to let you know, this whole chapter is basically the same thing. One section talks about means when you know the sigma. So what will you be able to use if you know the population standard deviation? We can use z-scores. One section is if I only know S, so I've got to use. And then the one section is if you want to talk about p hat. Right? So we'll attack that one last. That's kind of the newest one for us. Okay, so let's try this one. Page. I gotta tell you, some of these are really silly. Page 419, number. Oh, why? Number 14. Look how close we came to the magic number.
Yeah.
It's kind of freaky. All right. So this one says the health of the bear population in Yellowstone National Park is monitored by periodic measurements, blah, blah, blah. Thank God they put the bears to sleep first. A sample of 54 bears has a mean weight of 182.9 pounds. Assuming that sigma is known to be 121.8, use a 0.05, so blah, 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 blah. Let's kind of tear this down. Here's what you look for first. And this is sort of like how I teach word problems, even though this isn't a word problem. I try to tell my students the first thing you want to do is not look at all the numbers. You want to find specific things first. For us, we want to find out first off, what the hell is the claim? That's the most important thing. What is the claim? So can anybody tell me in this problem, And this problem is kind of nice. They tell you directly. Not all of them tell me directly like this one does. So somebody with a book. Number 14, what's the claim that they're making in that problem?
121.8 pounds.
That's not the claim.
Population mean of all.
It's too heavy.
Exactly. So the claim is that the mean weight of all these bears is greater than 150 pounds. That's great. If you're bookless, I'm not going to do that because I don't want to. So just take good notes. And we know that because in this problem it says test the claim that blah, blah, blah. In other problems it might say we want to show that the new drug decreases the amount of time from before. Then you have to say mu less than whatever. They're not going to say the claim is this, and neither am I. You got to pick out what the hell does somebody believe in this thing. Now the next step is to figure out the two opposing sides then. This is one of them. What must this be in opposition to? What must the other side think? If they're trying to prove that it's more than 150, the other side must feel the opposite of this. So these two sides are called hypotheses. One is the null hypothesis, also known as the HO. I'll say that, so I'll get it out there right now. And the other one is the alternate hypothesis, which in another book had HA, which makes more sense. And this one it's H1 for some damn reason. So I call it the HO and the high. So this is the null hypothesis, and this is the alternate hypothesis. Exactly. And some of you guys know that the null represents like the zero, the origin. So this is the null hypothesis, and this is the alternate. And you'll start to see that there are a lot of little parts to this, but every hypothesis test, I don't care what type of test it is, they all set up the same damn way. So it's going to take a little bit of a learning curve, obviously, to get used to this stuff, but it doesn't change, is the good part. You can always kind of find it the same way. One thing that never changes is that this guy, let me say it like this, this guy has to always have an equal sign. Equals, greater than or equal to, less than or equal to. Because this guy, he sets up what's called the rejection region. He sets up how far away I've got to get, that area that's going to show me something. So in this case, where would I want my sample to end up to show evidence that I'm right making this claim? Where do we want the sample to end up? Up here or down there? Above. I want it to be greater than 150. So that's why this guy is always going to have no equal sign. He's going to be specifically up, down, or there will be some cases where I just say not equal to, which could be either direction. So in this case, the opposite, what's the opposite of this? Less than or equal to. So the claim has no equal sign, it must be the high. Because it's very specific. It has to show me which way I've got to go to show evidence. So in this case, I want to go up, above 150 to show evidence for something. Yes?
So the claim could never be something like mu is greater than or equal to.
No, I want to be really careful here. I didn't put this here because it was the claim. I put this here because it didn't have an equal sign in it. My claim could be anything. But if the claim was mu equals 11, that would go in which one of these? The HO. Because again, what's got to be true about the HO? It's got to have an equal sign. Equal, greater than equal to, less than equal to, right? So what would be the high in this case? So the HO would be mu equals 11. What do you think the high would be? Does not equal 11. I love it. So to show evidence in this case, which way do I want my sample to be? Either way. If I think it's not 11 anymore, not 11, something else, then I can show it's up or down. I don't care. Kind of with me? Do you see how this leads to the t-score chart being set up the way it is? Why the hell do they have a row of one tail and a row of two tail? Well, how many tails would this be? How many tails actually shows me something in this case? One tail, I got to be greater than 150. It's a one tail test, whereas this would be two tail tests, kick-ass. So the t-score chart is set up beautifully for these hypothesis tests.
You have to do a, what was it called? I don't even remember. The NAB for that one? It was 11.
No, the NAB is only if I have P's and Q's. I'm not talking about means in that case. I'm talking about percentages. Yeah. Okay, so this is just a little side example. So coming back to this. This was my claim, just to make sure we all know. And I know it's going to be a one-tail test because of this. In fact, to be a little more specific, it's going to be up here. Okay. Step 2. Of course, this is going to seem a lot longer than these actually will be because I'm explaining the hell out of each step. There are 5 steps. You're like, oh crap, that was one step. There's a lot of me talking. It wasn't very long to set it up. There's a lot of me talking. Yes, Jeff, you talk a lot. Step 2 is what we really need to know that we can do anything else, and what we need to use to do anything else. Do I use a z-score, a t-score, or nothing? Z, T, or nothing. When would the answer be nothing? When can I do nothing? Well, I'm given everything I need. Everything I could need, I'm given. It's not normal, exactly. Sample size isn't big enough, or they don't tell me it's normal. We can't do anything, right? In stats 1, we can't do anything. So which situation are we in? What do we know here? Do we know the standard deviation of the population, or do we know the standard deviation of the sample? And is it normal? So first off, is it normal? Does anybody know if it's normal? This is number 14 on page 419. What would I look for to see if it's normal? Either they say this is normal, or what?
It's over 30.
Yeah, and what's the sample size? How many bears do they go out way? Yeah, 54. So normal, yes. N is equal 54, greater than 30. Central limit theorem says, go with me. And this problem is a really nice one to start with because they're really being nice. They give me the symbol of the stupid thing. You can't go wrong here. Do I know the population standard deviation?
Yeah.
Yes, they told me sigma. Check. So which one can I use? It is normal. I do know sigma, so which one do I use? Z-score. I love it. Cool. So step 1, what the hell are you talking about? Step 2, what are you allowed to use to talk about it? Step 3 and 4, we actually use this stuff, right? Step 3 is going to be setting up the rejection region. So this is the step that forever until chapter 8 has been 2 standard deviations away, sets up what's usual and unusual. In the real world, it can't be that cut and dry. It's got to be based on the situation. So if I have a situation where I have like normal levels in a nuclear power plant, I have an acceptable amount that they can go outside of those normal levels. I probably want to be a little safer, so I'm probably not going to say 2 standard deviations. I'm probably going to say more like maybe 1.28 standard deviations outside the normal. Are you with me? I don't want to wait till it's 2.575, and then just start pushing buttons. It blows up. It's bad. I want to say if it gets up to 1.28 above normal, screw it. Let's go take a look and let's see what the hell's going on. So it depends on the situation. How bad is it if you wait too long or if you're wrong? How bad is that? So that's why we should be able to change this. In this problem, they say this phrase, if I remember correctly, the level of significance, right? They tell us, yes, use a 0.05 significance level. This is alpha. That's another name for alpha. It's another name for that area in the tail or tails. So what is alpha in this problem?
7.5.
What significance level do they tell me to use? 0.05. Yeah, they say use a 0.05 significance level. So alpha is 0.05. How many tail tests did we say this is? One tail, because I have to be above 150. That's the only thing that's going to show me anything. So this is a one tail test. Alpha is 0.05. One tail test. I have enough information now to go find a z-score. Let me see if you guys are good with this. To find a z-score, I'm going to look at the t-chart. And I always have somebody go, what the hell? That's a freaking t-chart. Because on the t-chart, where are z-scores at? At the bottom. So if I look at the t-chart, let me see if I can do this without waking that dude up. Which one? Area in one tail or area in two tails? One tail. It's a one tail test. So if I go one tail has 0.05, that's going to be the second to last column. You guys see that? One tail, 0.05, second to last column. If I go down, all the way down, if I stop, that's a t-score. I want to use a z-score, so I go all the way down. The z-score you want to use. Beautiful, 1.645. I love it. I think the book uses the symbol ZC. The book really loves those freaking subscripts. I wish they'd just get over that. Of course, the minute I say that, I actually use a superscript here a little bit later, so it's too bad for me. So this is called the critical score. And that's kind of like my benchmark. And I like to use the example of if I'm a football coach and I need to get one more guy on my team and I have nobody that's really fast. I need to find somebody fast. So I set a benchmark. I say, I want you to run this far and this fast. And that'll prove to me that you should be on this team. So that's really what that is. That's a benchmark. It says you've got to find a sample that goes beyond this point to show evidence of what you want to show evidence for. In this case being greater than 150. How are we doing so far? So that can obviously change a lot. If they said alpha was 0.01, that would have been a lot bigger. It would have been a harder test to pass, right? The z-score would have been larger. So it depends on how bad is it to let it go that far. How bad is it to be that wrong or that right? You can control that level. So what's this picture going to look like? Where's my one tail? Which side?
Right.
Yeah, above. I want to be greater than 150. So this is what's called my rejection region. And why do I call it that? If I find a sample that's in there that's more than that far away, what can we say? Who can we say is wrong? The hope. So you gotta love this. If you find a sample that's in this region, you can reject the hope. Support the high. You found evidence that this is right. You found evidence that this is wrong. You kind of with me? That's why we call it the rejection region. You either reject this guy or you fail to reject this guy. If I got a 1.2, I fail to reject the hope. I fail to support the high. You kind of with me? That, of course, we're going to focus on because students have a lot of trouble with how do I word this thing? Which wording do I use in what situation? So I want to make that really clear at the end here. So right now we can say if, let me see if you guys can go with me. Let me say something right now, just to explain why I do this. There's going to be two z-scores in this problem. One of them is the benchmark z-score. Where's the other one going to come from? The sample we take. So the one from the sample, I actually call that Z star.